I can't find my pencil.
Right. So what do you see on your screen from the Zoom meeting? Do you see a simulator?
Yeah.
Yes.
All right, nice. Okay, now what is this? That's a magnet, right? Because you see it's north and south. So we have in magnets, we see magnetic poles, which is a north pole and a south pole. And also we do know that we cannot break the north pole or south pole and break the magnet and separate the north pole and the south pole. We can't do that. So there are no magnetic monopoles. But as you see here, hold on. Okay, so here's the North Pole and South Pole. So you know, like it's when you have a magnet, there are magnetic field lines that go around the magnet that's starting from North Pole and goes towards South. So basically when you are using the, when you want to find out the direction of magnetic field, so that's how you draw the magnetic field lines. So field lines start from north and it goes towards south. Now for our easy visualization and to recognize what is going on with the magnet, we always use our right hand and always your thumb is pointing from north towards south. So basically you need to place your thumb directing away from the North Pole. So basically your thumb should be pointing towards this way. I think you can see what I'm drawing here. I can draw a hand here, but if I keep my thumb, it should point this way. Okay, so from North Pole, this way. So, all right, so we understand that there are magnetic field lines around the magnet like this. Yeah, so I will ask a question. Are there any magnetic fields around these coils at this position? Your answer should be yes, because there's a magnet close to these loops, these coils, and there are magnetic field lines that's passing through this coil. Okay, now here we have a bulb and a voltmeter, and there's no battery, so there's no way that I can lit the bulb. But observe this, when I move the magnet, when there's a movement in the magnet, I can light up the bulb, right? You see that? But there's no battery. So it's happening due to this motion of the magnet, right? When I hold it still, there are magnetic field lines, but there's no current that flow through the circuit to light up the bulb. But whenever I move the magnet, I can light up the bulb. Okay. Even here, I can move the magnet around this loop and I can make the bulb lit, right? So we're going to learn about this theory today. So that's the main plan. But before that, we need to understand what is the magnetic flux and what's the magnetic field. Okay. So we do know magnetic field. So for this magnet, in this picture, you see about 1, 2, 3, 4, 5, 6 field lines over here. In this area, there are 6 field lines. However, through this coil, I see only 1, 2, 3, 4 pass by. But when I bring the magnet closer to the loop, all the 6 and also these 2, also 8 magnetic field lines are passing through the coil. So we say the magnetic flux is large here. But even though you keep the magnet farther away from the coil, there are magnetic field lines that passes through the coil, but number of field lines that passing through the coil is less than we keep the magnet closer to the coil. Okay. All right, so I'll take my PowerPoint slide open and let's learn from that. So this is where we stopped last week, learning about magnetic fluxes. So magnetic flux is not just the magnetic field lines, but we need to count the area of the coil, the magnetic field strength, and the angle that whatever the coil that placed in the magnetic field. So the flux symbol is this Greek letter pi, and we put B to indicate magnetic. So phi B means magnetic flux. That's equal to the magnetic field strength measured in Tesla. A is the area, it's meter to the power 2, and cos theta does not have units, but we use the theta in degrees. So its flux is BA cosine theta. Okay, so the symbol for magnetic flux is this symbol pi. The units for magnetic flux is Weber. Okay, so mathematically, cosine theta, we take it to be 0 degrees. So it is cosine 0 is 1. So you can try it on the calculator. Cosine 0 is 1. So if you remove that, the flux will be a magnetic field times the area. Okay, so we can know the angle between the magnetic field and the loop area, and we can calculate cosine value. So here, flux is measured in Webers. It is WB is the symbol, and B is measured in Tesla T. The symbol for Tesla is T, and A is the area over which the magnetic field is acting. So it's square meters, so meters to the power 2. So Weber per square meter is the flux density. So if you want to calculate the density of flux, then it's Weber per square meters. All right, so now look at this bunch of pictures here. So you see, like in the top picture, we have 1, 2, 3 arrows that represent the magnetic field lines. So there are 3 magnetic field lines passing through the coil. So this black color ring is the loop. And here in this one, we have 1, 2, 3, 4, 5, 6 magnetic field lines passing through the loop. So we say that this second picture onto the right, it does have a high density of flow of magnetic fields. Okay, so it have a high magnetic flux. Now let's look at this second row pictures. So in the second row, you see 2 pictures here. The only one difference there is the angle the loop is creating with the magnetic field line. So this one is a little angled to the right side, but this one is straight, like in 90 degrees with the magnetic flux, magnetic field lines. So as you see here, the flux that goes through the boundaries of this loop is changing according to the angle. And over here in the third row of the pictures, you see like there's a small area that's covering by the loop, but this one is a larger area. So it's this one, the second picture to the right, it can grab more magnetic field lines into there. So there are high magnetic flux going through this loop. So we say magnetic flux density is higher in this picture. So among all these pictures, the pictures onto the right side does have a high magnetic flux density going through the loop. Okay. So the flux can change if the area position relative to the magnetic field changes, and also if the that means the angle and the size of the area that you're considering. So that gives us the idea about this, how to generate electricity using this change of the magnetic field, as you see on the simulator. All right, so Faraday's law. The Faraday's law described about the electromagnetic induction. So induction means it's creating something, right? So if you remember our first chapter about electrostatic charges, so we induces current or induces charges on the surface, right? So likewise here, we're going to induct electricity by changing the magnetic fields. So you notice on the simulator that we can produce electricity by moving a magnet. So if we ask the question like, can magnetic field produce electric currents? So answer should be yes by our knowledge from the simulator. So Faraday is the first person to try all this stuff. So he in the beginning, he was not successful detecting a current that going through the coil, but suddenly he moved the magnet and he noticed that there's a current induces in a secondary circuit. So from there, the theory being developed. Now we have this Faraday's law in place that we can use for many applications in the nowadays technology. So the primary coil was connected to a battery to produce a current, and there was a secondary coil that did not connect it to a battery, but it induces a current, like in that simulator you noticed earlier. All right, so like this experiment. So in a real class, I would bring a coil like this. This is just a coil that's a copper wire wrapped around here in a shape of a cylinder, and it's connected to a meter where we can read the current going through the circuit. We call this as a galvanometer. And we do have bar magnets that we can move it around this coil. Okay, so Faraday is the one who noticed this for the first time, but now we can observe it by doing little demonstrations. So here, if we move this magnet around the coil, I mean through this coil around here, we can see that it is inducing a current. So there will be a deflection in the detector over here. So this is a galvanometer. So the galvanometer indicator will deflect left to right depending on which direction you are moving the magnet. So Faraday also detected a current in a coil of wire when a magnet was moved into or out of the center of the coil. So we can find out the direction of current. We will try it today, hopefully. So the galvanometer deflect one way when the magnet was being inserted and the opposite direction when it was being withdrawn. So that's why I mentioned like the induced current direction, it's depend on the direction that we are moving the magnet. Then no current was detected when the magnet was not moving. So if you remember from the simulator, when I hold the magnet there are magnetic field lines around the coils, but it did not induce a current. We were not able to make the light, the bulb light up, right? So there should be a movement to the magnet. So an electric field is produced when there is a changing magnetic field. So this is a very important word, changing. So there should be a changing magnetic field to induce a current or the electric field. Okay. So Faraday law says the induced EMF or the induced voltage is equal to change in flux over time. So this is the base equation. From what we have observed, we should be able to produce this equation, but we are not going to develop the theory here. We're trying to learn the theory that's available. So this is the equation. So voltage or the induced EMF, electromotive force, is equal to changing flux over time.
Excuse me, can you go back one slide, please, real quick?
Say it again.
Can you go back one slide, real quick, please?
This one?
Yes. Thank you.
Can I move on?
Yes, I got it.
All right, so there will be an induced voltage or induced current or induced EMF in a circuit when there's a change in magnetic flux passing through the circuit. So this word change in magnetic flux is important. So not a magnetic flux, but change in magnetic flux. So when we move the magnet around, we are making a change in the magnetic field around the coil or whatever the place. So the induced voltage is equal to the rate of change of magnetic flux. Now, you might get confused with these wordings, but look at this equation. It's changing flux over time. So it is, you are dividing something by time. So we basically calculating rate of change, right? So we call this as rate of change of the value on the numerator. So it is rate of change in flux, okay? Don't worry about this equation. If you're using in the textbook, you will see these equations. Delta, we always use delta to indicate a change, okay? So change in flux over time. That's the induced EMF symbol. So this process is called electromagnetic induction. inductance, induction. So it is electromagnetic induction. So electromagnetic induction means you are making a change in the magnetic flux around a coil and induce a current on that coil. Okay, so we learned that the magnetic flux is a measure of how much magnetic field lines that passing through the coil, and it is at a maximum when the field lines are perpendicular to the plane of the loop. So here, if you keep the loop along the magnetic field lines, then there's no magnetic flux passing through the coil. But if you keep the coil in perpendicular to the magnetic field lines, then we see the maximum flux going through the loop. So we can induce a maximum current in this position. So for a coil of n number of loops, so n means how many number of loops are there. So if you remember from the simulator, the loop that in the bottom it had more number of loops than the top one. So whenever we have higher number of loops, then the flux that going through the coil is equal to the flux through one loops, multiply the number of loops. So if you have high number of loops in a circuit, then we can induce a more current, detecting from the other one. All right, so this is a sample picture of a like inducing current onto a secondary coil. So as you see here, I'm not talking about the middle loops with the blue color lines. That's represent the magnetic flux that passing through the coil, but I'm talking about this orange color loop here. So there's an orange color coil here that's connected to a battery, and there's a switch. So we can send a current through this coil. And once you send a current through this coil, you will see an inducing current on this circuit. See, like this circuit is independent from the battery circuit. But when you connect like this, you will see an inducing current on the galvanometer, on the secondary coil. So we call this as the primary coil, and that's the secondary coil. So an electric current is only induces in the secondary coil when there is a change in current in the primary coil. So this is a transformer. So here we don't see any magnets, but when we send a current through this coil, it will induce a current in the other coil that's independent from the primary coil. So the secondary coil will display some current through it. But as you see here, you don't see a magnet, but there's a current going through the primary circuit. So when there's a current, there's a magnetic field. If you remember last week lecture, so when there's a current going through a wire, there are magnetic field lines that's created around the wire, right? So here there's a coil. So current is going through, it is inducing a magnetic field around it. That magnetic field will effect onto the secondary coil, and there will be a current going through the secondary coil as well. So that's the theory of generators and transformers. So in transformer, you will see a primary coil and a secondary coil. So in a generator, it converts mechanical energy to electrical energy by electromagnetic induction, and it produces an alternative current. So in this picture, this is an old-fashioned cranky generator. So when you move this handle, you can light up the bulb, even though there's no battery connected to this one. Okay, so you rotate this little handle. It's a mechanical piece, but here you have an electrical piece with the bulb on it. So when you rotate this, you're cranking it basically, so you can light up this bulb. So mechanical energy converted into electrical energy. Then a simple generator consists of a coil of wire that generates an electric current when turned between the poles face of permanent magnet. So inside here, there's a permanent magnet. So when you rotate this one, that magnet is rotating around the coil in changing its direction regularly. That will induce a current in the circuit. So the coil rotation causes the magnetic flux through the coil to change continuously. So that change due to the rotation of magnet create a change in flux that's help to induce the current in the secondary coil. So it is the changing flux that produces a current in the coil. So remember, in summary, so when there's a change in flux through a loop, I mean change in a magnetic flux through a loop, it can induce as a current. So we call this as the induced current by the changing flux. All right, so we learn about AC current. So AC means it's alternative current, right? So alternative currents means it's changing its direction regularly. So it's change. So there's a change in the current that going through the circuit. So it can induce currents. So here in this picture, you see the top graph. Here we have flux and here's the time. So flux is changing over the time. That's why you see this curvy direction. And here, this is the EMF or the voltage on the y-axis. So you see the voltage also changing according to the magnetic flux here. So let's look at what it is. So the flux changes continuously from a maximum value in one direction, then to 0 to the maximum. So that's what mentioned in this graph. So it's starting from 0 and in positive direction, or let's say this upward direction is positive. So in the positive direction, it goes to its maximum magnetic flux, and then it's come back to 0. Then it's go back again into higher number in negative direction all the way down, and it's come back to 0 again. So this change is keep happening. So the it will induce a voltage in a secondary coil. So as you see here, the induced voltage also depends on the rate of change of the flux. So it follows the pattern of the flux, and it will induces a current like this. But if you look at it close enough, you will see the pattern looks identical, but there's a little shift in the time axis. So let's say like here, you see a 0 flux, but here you see the maximum induced current. Here you see a 0 flux, but you see the negatively maximum flux. So that's because of the change. So there should be a change to induce current, right? So the change is maximum when it's changing its direction. So here it's come to 0, but it's changed the direction to the negative side. Over here it is positive direction, here it is negative direction. So when it's changing its directions, it induces the maximum current that possible. So here we see the maximum current that induces in the circuit. So when the flux is increasing the fastest, the voltage is maximum. When the flux is decreasing the fastest, the voltage is minimum in the other direction. So it is in the negative direction, maximum here. Okay, so these are a couple of pictures that you can see the transformers in your community. So a transformer adjusts the voltage of an AC circuit up or down as needed for a particular application. So the transformers are seen on utility poles at electrical substations and as voltage adapted for electric devices. And the ability to use generators and the transformers mean that alternative current is convenient for large-scale power production and the distribution. So in many places that we have high voltage lines, we'll be seeing these transformers. So the transformer uses the current that's incoming current, and it's converted or induce a different current into the secondary circuit, giving us a low voltage amount to our houses. So in the main line, there's a high voltage line, but using these transformers, we can reduce the strength of the EMF, and we are receiving that particular 120 volts into our houses.
That's not my drink. Oh, are you sure? I'm pretty sure that I remember making your drink and using the sticker on it. You know, can't be mine. Yeah, no, this is definitely yours. It has the caramel on the top. I can't take that. Huh? You put your fucking nose in it. Oh my god.
All right.
I will totally make your drink for you.
Yeah, that's my favorite show.
Yeah, who is... If you are in personal communication, please mute yourself, because we don't need to listen to your communications, right? I know it is online. It might be boring to listen to me for a couple of minutes, but this is the important part. So I will go over the lecture for about 10 to 15 minutes. Then I'll give you a chance to work on the questions, right? So you should be able to bear on me and spend a little bit time listening to my boring lecture. You are in a university, right? So there are professors who keep talking. So we have a bad habit of talking to ourselves, assuming that you can understand. Maybe you cannot. Still, we want you to listen to us because you are in a college, and our job is to show you things, and your job will be to investigate more in that topic and get more deep understanding. But okay, so this little triangle represents change, and we call this as a delta symbol in Greek letters. So this is delta, that's represent the change. Name is delta. So delta V1. Delta V1 means the voltage across the primary coil. That's equal to the number of coils in the secondary coil divided by the voltage, that change in voltage in the secondary coil. So delta V2. So if we have numbers, we can easily plug it in here. So let's say delta V1 is 10 volts. And if we know the number of coils here, number of turns in the coil, then we can calculate the inducer's voltage amount. Okay, so this comes in symbols. I didn't use numbers here, but in the practice questions, we will use numbers and do calculating. So here's the equation. You will say, oh, you're teaching algebra. I'm not. This is just a relationship between the values. Okay, so if I write like 10 equal 5 times 2 or something, that does not make sense. It's just a number equation. But here, for this equation, it does have a lot of information there, because I can change the voltages and I can calculate like what are the number of turns ratios that I need to induce this much of current. So this is a very important equation. Okay, so again, what is delta V2? What do you think? You can
The secondary coil.
Voltage in the secondary coil, delta V2. 2 means the secondary, delta V means the voltage. Okay, it's equal to delta V1, that is the voltage in the primary coil. Okay, and N2 is the number of turns in the secondary coil, and N1 is the number of turns in the first coil. Okay. Okay, so what do you think? Can a transformer be used as shown in the diagram below to step up the voltage of a battery? Okay, so look at it closely. So here we have a battery that's connected to a primary coil, which has only 1, 2, 3 turns. Now here we have a secondary coil with high number of turns than the first coil, and it's connected to a resistor. Resistor means a battery. So the question is asking, can we transform, this transformer be used to induces a current on this one with a step up, so increases the battery voltage. So what do you think?
Yes.
Yes. I think someone might say no. Impossible to tell from the figure because voltage values or the current values or the number of turns wasn't given.
See?
Okay, that is the confusing part of physics, right? So we feel like, oh, we understood it, but when we're answering questions, we feel, oh, we didn't get it. So something is wrong, right? So here, the answer should be no, because it will not work as shown in the diagram. If one contact of the battery and the primary were to be continuously open and closed, this would produce a variable flux in the transformer would work. Here, look at this battery. It is directly connected to the primary coil. It is a DC battery, so there's no change in the flux. Now let's go back to the theory again. Look at this one. Or maybe our first picture with the coil. Where is that? This one. Look at this. There's a switch that we can open and close. Open and close. Then it will induce a current. But when we keep this one closed completely, then there's no change in flux, so that we cannot induce a current. Now, let me take you back to this figure here where I talked about the theory. Look at this one. This is something that I didn't mention. I should have mentioned it, right? So here we have delta V1, and look at the variation of delta V1. So here I'm trying to teach you how to read a picture with appropriate values. So here we have delta V1, and here's the time. So you see, like delta V is changing over the time. So there's a change in the voltage that we are supplying to this circuit. It's a change in, it will create a change in flux, right? Now, it will induce a current on the second circuit, which follow the same shape. So in the question, the only issue here is over here. It's okay, we have a primary coil and a secondary coil, so it should able to induce a current on the secondary circuit, but there's no change in the electromagnetic field over here to induce a current. Okay, so there should be either a switch, or we need to make this as an AC current. This is just a DC battery, so it can't induce a current. Okay, I think we should try top hat and then come back here. Maybe let's talk about this one, then we'll move to the top hat so I can do a couple of questions on this law. Okay, so Lenz's law supports the earlier idea. Okay, so look at this picture. So we have a loop over here, orange color loop, and here's a magnet. So we can move this magnet either towards the coil or away from the coil. But according to this picture, there's motion of a magnet that's going down, right? So the north pole of the magnet is moving towards the coil. That's what it mentioned. So it's going towards the coil. So as it goes towards the coil, there's a change in magnetic field because I'm moving it around. So it will induces a current in the circuit. So there will be an induced. Now, what is the direction of this induced current? In the picture, we see it's going towards this way, right? So if you look from the top, like eagle eye view from this side, then you will see it's going towards the counterclockwise direction. So if you look at it from the clock, like in a wristwatch, you will see the dial is going in the clockwise direction. But if you look at the opposite direction, we call this as counterclockwise direction. So here, according to the picture, the magnet is moving downward, having north pole downward facing, and there's an induced current that's go in the counterclockwise direction. Okay, so think about the direction of current here. It is counterclockwise. So basically you're looking from the eagle eye from the top here, and you compare with the dial of a wristwatch or a clock. Okay, so the direction that the hands of the clock ticking is the clockwise direction, other opposite direction is counterclockwise. So the direction of the induced current generated by the changing magnetic flux produces a magnetic field that opposes the change in the original magnetic flux. Okay, so this is a natural theory. Now, here's a loop, and there's a magnet that's coming towards the coil, and coil doesn't like it. The coil need to stop that effect. Think about if someone push you, then you want to get rid of that push, right? So you will be acting opposing that push. So you will be pushing it away, right? So likewise, this coil does not like this effect. So you see like there's a magnetic field comes towards the coil and coil doesn't like it. So coil try to do something and create a opposite direction magnetic field to stop this effect. Okay, so now what is the direction of magnetic flux coming from, magnetic field coming from the magnet? It's not down, right? So basically the magnetic field is facing down. Now to the coil, it's feel like there's a magnetic field comes downward. So coil doesn't like it. So coil try to create a current that going through the coil and create a magnetic field to oppose that effect. So the external field that's coming from the movement of magnet is downward. So the coil will create a magnetic field that's flipped, opposing that effect. So there should be a magnetic field that's going upward direction. So in order to have a magnetic field that's going upward, there should be a current going through the loop in the direction that your forefingers are curving. Okay, so let's do this. Use your right hand, keep it in front of the computer screen. Now, keep your thumb in the direction of the North Pole. So North Pole of the magnet is downward, right? So you keep your thumb facing downward. So that is the magnetic field that's coming towards the coil. Okay, so I think you can see my screen, my video. If you don't, you can make it to the speaker view so you can see the video of the person who's talking. So at this point, I'm the only one who's talking, so you should be able to see my video. All right. So here's, let's say this is the coil, and here's a magnet with North Pole down. So here the coil will see there's a North Pole coming downward. Okay. This is the direction of the magnetic field that's coming from the magnet. Now, this coil doesn't like that. So the coil will try to create a magnetic fold that's facing north up to avoid that effect. So there will be a magnetic field that's going up. Again, you use your thumb to indicate that induces magnetic flux. So magnetic flux will go upward, let's say magnetic field. So magnetic field is going upward. In order to have a magnetic field that's going upward, there should be a current that induces in the loop. So it will be curving. I think I will keep it like this. So the thumb is coming towards you. Now you're curving your fingers on the four fingers along the loop, right? So for you, you should be able to see like it's going in the counterclockwise direction. Okay? So this picture is correct. So you see a counterclockwise current going through the circuit, opposing this effect that came from the motion of the magnet. Okay, so the applications, you know, the credit card reader. So in this type of credit card reader, I'm not talking about the clip one, I'm talking about this sweep one. So you have to sweep it, right? So sometimes it does not read properly if we didn't sweep it properly, right? So there should be a change by dragging the credit card through the reader like this. So that's happened from that above theory. So the credit card has a magnetic strip on the back that has regions of alternative magnetization. So when you sweep the card, that moves this stripe through the circuit of the reader, then it will induce a current onto the card reader, so it can read the credit card number for you. So for each of you with the different credit cards does have a different pattern in the magnetic stripe on the credit card. Yeah, I'm talking about this stripe. Right? So this strip is a magnetized strip. So according to your credit card number, this will have a different pattern organized inside. So when you sweep it through the credit card reader, it will induce a current according to the magnetic field change happens according to your number, and it will induce a current in the circuit and it will read it for you. All right. Then other application, maybe you have seen these magnets that you can attach to other metal pieces. And this is another application. So in the trash dumpers, they're separating this magnetic field by using electromagnets. So they will be moving a magnetized object closer to to detect the metal particles. So this is a magnetized disc. So it is an electromagnet that you send the current through it and create a magnetic field in there. Then you catch the metal pieces, then you will move it to a different place and switch off the current. So you remove the magnetism in the disc and you can let the metal pieces go. So this is a metal detector. So you can detect metals using an electromagnet. But if it is a permanent magnet, it will grab it and you cannot remove the metal pieces. It's hard. You should find a different way to remove it. But in an electromagnet, that's this one, the the one in the top over here in the picture, you can control it by using the current that going through the circuit. So when you switch off the current, there's no magnetic effect coming from the field, so you can let the metal pieces go away from that. So that's how the metal detectors work. And the CD. So inside the CD, this is a cross-section diagram of the little tiny area over here. So as you see, it's organized like south, north, little magnetic pieces, right? So these are magnetic pieces. Now look at the size. So this is the 0 digit and this is the 1 digit. So 1 digit has 2 magnetic pieces here. Here it is just a 1 magnet piece, south, north, then north, south. So this is the arrangement of 0, 1, 0 digits. So the inside the CD, we create these magnetic patterns. So depending on what you are writing on the CD, this pattern will vary. So when you have the reader in there, it reads these, this detector, this one, the handle will move along the magnet pieces and it will read, it will induce a current and it will read the whatever the value in there. Then it does conversion of the current into a vocal or the sound waves. Anyway, so the inside the CD, it uses these magnetic patterns and it uses the theory of inducing current in there. Okay, so you may have noticed that the arm of the CD reader is rapidly moves, right? And it's keep moving. So it's create a change in the field. So when there's a change in the field, it will create the current. It will induces a current and you can read it, and then the machine will convert that electric current into a sound wave. So you can hear this music or whatever the recorded in there. And the computer hard disk store information using magnetic fields as well. So whenever you enter data or save it, it reads the 1010 digits, but it's always create the magnetic pieces like this and create this data saved onto the device. Then the speaker, you know, like you're using your earbuds, that uses the inducers, this theory of inducing current by changing the magnetic field. Actually, if you're in a real class, I will show you the real picture of this. So this is just a petri dish, and here's a coil that attached in there. It's a copper wire that's wrapped around this plastic piece. And on the top of the lid, I created a small magnet. So when you send the voice or the recording of something vocal voices, there will be a change in the voice. So it will create a change in the magnetic field on the top, and it will vibrate and you can hear it. So this is how the speaker work. I added a link to my video. If you can't see it, you may watch it at later. And also you should be able to hear it. So let's see whether you can hear it. So here's the petri dish, and here's a copper wire wrapped around the piece here. Okay, so let's watch this. And on the lid, here's a tiny magnet there. And we close it. And here I'm going to plug that into my phone outlet. And then I connect it. Do you hear Ghostbusters? Okay, here we open it, we can't hear it. But when I close it, I can hear the sound, right? So this is how a speaker works. Okay, so this is a real demonstration that we would have been doing in the class. So we have a petri dish and a copper wire, and this wire is connected to the phone or other device voice outlet. And then we have a magnet on the top dish, and when the voice going through it, it vibrates and it creates the magnification of the volume of the voice. Okay, so that's how the speakers work. All right, so next a couple of the slides I have some information about the electromagnet, so I want you to read those after the class today before you do the next homework. Okay, not bad. So it's 10:30. Let's try questions on top pad and I'll take your attendance. And on Thursday, I will open the next homework. Today I have an appointment with VCU IT support, so they will resolve the problem for sure. Then I will open the homework, but I will send you an announcement once I open it. Let me find my- Okay, so send me the attendance code. Yeah, we already completed homework 1 and 2, and next one will be third homework. We are planning for about 10 homeworks for the semester. So I think we are in a good track, even though I didn't assign something last week. All right, so I'll keep it minimized and let's start the presentation. All right, so this is not about like testing your knowledge, but also learning something new, right? So this is a picture of a simple electromagnet. See, like a battery and a nail, and we have a copper wire coiled around the nail. So it's asking, how can the electromagnet be made stronger? So, you know, like it's what is the electromagnet? So when you're sending a current through this wire, so there's a current going through the wire, then whenever we have current going through a wire, it induces a magnetic field, right? So this area will be magnetized due to this current that going through it. Okay, so we can create these electromagnets at home. So if you have a galvanized nail and a copper wire and a AA or a AAA battery, then you can create a magnetic field around this wire. Yeah, if you are facing problems on TopPad, you need to talk to the TopPad support and resolve the problem, because I don't have any control from your device. So you should get help from TopPad support. Also, you may sign out and sign in again or refresh the browser maybe. That will resolve problems on TopPad. All right, so the answers given are: add more coils of wire to the nail, remove all the coils and the nail, use a smaller battery, reverse the poles of the magnet. Okay, so in this picture, there's no magnet, but we have a nail and a wire and a battery. Okay, so there's nothing to do with the magnet here. Reverse the poles of the magnet, but I do not have a magnet here to reverse the poles. Okay, so we are going to create a magnet by using the wire, nail, and a battery. All right, so let's look at your responses. Yeah, nice. Yeah, so the correct answer is add more coils of wire to the nail. So when you increase the number of loops, it will induce more magnetic field around it. Okay, so B, remove all the coils and the nail, then there's no electromagnet. You remove all the coils and the nail, then that's just a wire. So there will be a magnet, but it's not an electromagnet to create the magnetic effects in there. Then use a smaller battery. This means the smaller battery, I should have worded it differently, like a low voltage battery. So smaller battery means a low voltage battery. So if you're supplying a low current, then induces magnetic field will be smaller as well. Delta V, in that equation, delta V, if you reduce the delta V, then the induced current will be smaller. Reverse the poles of the magnet. Yeah, as I mentioned, there's no magnet here that externally affecting the system. We only have a current carrying wire and a nail. Nail is not a magnet. We're going to make it magnetized. Okay, so answer D is incorrect. Okay, so are we all good in sending the attendance code? I'm going to finish counting attendance. If you need more time, you need to tell me now. All right, so I'm going to finish counting the attendance. Okay, this is a quick question. It's straightforward. So I'm going to close it really quickly. So what are the ends of a magnet called? What are the names of the two sides of magnet? Okay, so let's look at your responses. Yes, that's great. So I believe 99% is with me now. Okay, this is a tricky one. You need to use your right hand and think about what's going on here. And I'm going to help you here at the end. But first, I'd like to give you a chance to think about it. So what is the direction of the induced magnetic field? Hold on. Please stop because I need to edit it really quickly. Give me a second. So I'm going to stop counting it. Hold on. Because it's need to be edited. Give me a second. Okay, so now you can see the question because I close it, but let me open it again. Sorry about that. Start presentation. Okay, now I'm open again on top hat. So yeah, if you already answered, please retry it because I changed the question a little bit. So what is the direction of the induced current? So that means what is the deflection of this indicator? Okay. So if you answered earlier, please try it again. So it's asking like, what is the direction of this hand? So will it go to the left, to the right? Okay. Looks like everybody send your answers. So let's look at your responses. Then I'll go over with you. Yeah, so most of you got it. That's great. Usually this is a tricky problem. I wish you didn't answer it randomly. I believe you understood how it's work. Okay, so in the exam, I might give you a question very similar to this one, but I will move it like maybe dragging the magnet other way around or switch the direction of the poles, like you're having South Pole over here, right? All right, so let's see how did you get it. So the first thing you need to think about when you see this type of question is you need to look at what is the direction of the magnet. So you see like south on this side and north on this side. So there's a magnetic field that goes towards the left. Okay. I'm not sure you are seeing my mirror image of my direction. So you need to think from your side. So look at the screen and think about what's the direction of the magnetic field. So it's going towards the left. Okay. Now it comes towards the coil or the coil over here, right? So the magnetic north pole is coming towards the coil and coil doesn't like it. It opposes that. So to oppose it, it should create a north pole on this side. Then it repel, right? So the coil going to opposes this north pole that coming towards it. So it does need to create a magnetic field that opposes that. So the magnetic field that's induces by the coil should be in opposing the north pole that comes towards the coil. So there will be a magnet that faces north pole towards the incoming north pole here. So there will be a north pole in this side and south pole on this side. Okay, so north pole on this side and south pole on this side. So now you use your right hand, you keep the thumb towards left, and then you curve it around the coil. So there's a current that goes in upward direction here on the coil. So it's going upward, upward from this side. Then it's come down here. Then it goes through the detector. So the detector will turn left. So there will be a current that goes towards left on the bottom part over here. Okay, so answer is left. So I believe most of you understood it and answered correctly and try to understand the theory there. Okay, all right. So if we have a north pole, south pole, that's magnet. Now in this one, it's coming towards the coil, but if it's go other way around, so north is going away, so it's not approaching, it's going away from the coil. So the magnetic field is in the opposite direction, so the coil will behave differently, creating a different pole. That's to bring back the magnet. Okay, so that question will be on the homework, so you may try. Now it's asking what is the direction of the induced magnetic field. Okay, it's not asking about the current, it's asking what is the direction of the induced magnetic field in the coil. So you need to see like north pole and south pole, and the north pole is going away from the coil. Okay, so let's look at your responses. Okay, now there's a quite variation here. Okay, so first read the question. So it's asking what is the direction of the induced magnetic field? Okay, now here there's a magnet. North pole is facing down and the south pole is facing up. Now the magnet is moving away from the coil. It's departing, right? So it's departing from the coil. So there's a north pole over here, but the coil doesn't like it to go. So coil want to bring it back. So if the coil want to bring the magnet back, then there should be a south pole created over here. So south pole over here. So if there's a south pole over here, then the north pole will get attracted. So it's get towards the coil, right? So here this magnet, sorry, the coil try to create a south pole on the top and a north pole on the bottom. So basically it needs to create a coil, sorry, a magnet. I'm so sorry for the inconvenience here. All right, so again, so here's a coil and the coil see a magnet going away and there's a north pole over here and a south pole over here. So the coil doesn't like the magnet to go. So coil try to create a magnetic field in a way that it can bring the magnet back. So in order to bring the magnet back, there should be a south pole here because south-north attracts, right? So the coil try to create a south pole over here. And when it's create the south pole in this side, there will be a north pole created over here at the bottom of the coil, right? So the north pole and south pole. So basically it will have a magnet in the similar fashion like this. So the north pole on the bottom and the south pole and the up. So the magnetic field is down because always your thumb pointing to the north, right? So the down. So the magnetic field created by the coil or the inducers on the coil will be downward. Okay, so in this topic, the tricky part is to think about like what is the initial condition. So whatever given in this picture is the initial condition. So there's a north pole and a south pole. North pole is in the direction of coil. So this is the initial condition for the coil. Now the magnet is moving up. So taking the north pole away from the coil. So coil doesn't like it. So coil try to create a south pole on the top to bring the magnet back. Okay. Okay, so here's a quite a variation here. I still have answer right. I don't know what you mean. What are you trying to check here? Because right direction, right means towards this way, right? So it's not because north and south pole. So in the magnet, the magnetic field lines goes from north to south. So it's always pointing in the north direction. Okay. Okay, so it's 10:45. So I like to